Hello, welcome back. Today we're going to learn how to use change of variables to evaluate an integral. And now we have two integrals provided to us. As they are, there's no way to use the differentiation formula card to grab the formulas for, because we don't have any formula to take care of these integrals in one shot. So what we're going to do here is that we're going to smartly use the change of variable. We're going to define a variable in terms of x, and we're going to use the differential idea. We're going to rewrite this integral with the new variable, and hopefully that integral is going to be integrable. And let's see how we can sort of like choose the new variable to start with. So now the question here is that if there was no 4 over x squared, and if there was no 4 over x here, if it was just cosine x integrated, then we would be able to use the differentiation rule for cosine x, and in fact the integral would look like sine x plus c. And as you see that the inner part of cosine has something to do with the outside term here, because if I take the derivative of 4 over x, I'll get something like a number divided by x squared type term if you use the power rule for differentiation. So I think it's a good start that I call the inner part of cosine to be u, a new variable. And then what we're going to check now is du, and du is, in fact, u prime times dx. Okay, so I'll take the derivative of this function here, but this is equal to 4 times x to the power of minus 1. And if you use the power rule for differentiation, so the derivative is going to be minus 4 x to the minus 2 dx. Okay, but in short, you can write it as minus 4 over x squared dx. So this is exactly what du is, differential of u is. So since we are already defining a new variable, so we're going to convert this integral, or we're going to rewrite this integral with the new variable. So we're going to have the u term all the way multiplying a du term. So in other words, the new integral is going to be an integral. So let's check what's going on here. Well, first off, I labeled inside of cosine, the inner function here, u. So I'm going to have a cosine u for sure. And then you have, as you see, 4 over x squared, right? 4 over x squared. And then you have the dx here at the end, right? So these two is very similar. So the 4 over x squared times dx is in fact what you have here up to the sign. So why don't I put a plus sign and put a minus sign here? That means I'm multiplying this equation by minus 1. So in other words, 4 over x squared dx becomes negative du. Here we go. I have du here, but it's in fact negative du. I put a negative sign here. So in other words, I'm trying to integrate minus cosine u du. All right, so the rewritten integral in terms of the new variable u is sort of like way easier to handle than the original integral, because we know how to take care of the integral of cosine. That's in fact sine u plus c, but you have a minus sign, be careful. So minus sine u plus the integration constant. So, well, the original integral is given in terms of x, and u was sort of like the auxiliary variable. So why don't we go back to the original variable and conclude that that integral is in fact minus sine 4 over x plus c. So as you see that the whole rationale of changing the variable during the integration is that we convert the given integral to something really easy so that we can use the differentiation formula card to integrate in one shot. All right, for part B, let's stare at the integral of the function here. So as you have x to the 5th plus 1, and as an exponent of e, you have x to the 6th plus 6x. So now we should think like this. As you see that this x to the 5th plus 1 is sort of like an extra term. If that term wasn't there, and if the top is just x, this would be the integral of e to the x, and we would be integrating that without a problem. But the top is not x, and then you still have the tail term here, x to the fifth plus 1. So we somehow need to define a new variable so that we convert this integral to something that we know how to integrate. So the good news is that x to the sixth plus 6x has something to do with x to the fifth plus 1. I'm not sure if you have observed this, but if you take the derivative of the exponent here, so that's me calling the exponent to be u to start with, and look at the differential of that, meaning that I'm going to take the derivative of this. Let's see what's going on here. Du is going to be 6 times x to the fifth plus 6 by using the power rule for differentiation, right? So we put the exponent down, subtract 1 from the power, and do the same thing for this term here. So you have 6 times x to the fifth plus 6, but 6 is a common factor here, so why don't we pull that out? So I have 6x to the fifth plus 1 dx. This is sort of like the connection between x to the sixth plus 6x, which is in fact the exponent of the e here, and this term, because x to the fifth plus 1 dx is going to be 1/6 of du. In other words, if we divide both sides by 6, so that x to the fifth plus 1 dx is going to be replaced by 1/6 du after we have this change of variable. So in short, we're going to write 1/6 times du, okay, 1/6 times du. I put the du at the end because that's how the integration formalism works, okay? And then you have e to the power of u. And then where is x to the fifth plus 1 dx gone? Well, that's replaced by 1/6 du. And in short, you have 1/6 e to the u du. If you pull out 1/6, you just need to worry about this simple integral, e to the u du. And we know how to integrate this because this is in our integration formula card. And this is, in fact, 1/6 e to the u plus the integration constant. And the original equation has only x as the actual variable, so you have to go back to that because u is sort of like an auxiliary variable that we're using to convert this integral to something that we can integrate easily. So we have to go back to the original variable x, and u is x to the sixth plus 6x, and here we go. So the antiderivative of this chunk here is, in fact, this function plus c. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.